Yes, increasing the Hertz will increase the revolutions per minute or RPM of the motor, assuming it's within its designed operational parameters. Hertz is the unit of frequency and measures the number of cycles per second. For AC motors, the frequency of the AC power supply dictates the motor's speed. A higher frequency will result in a higher RPM. So, what exactly is Hertz? Well, Hertz is the unit of frequency, representing the number of cycles of a repeating event per unit of time. It is named in honor of Heinrich Hertz, a German physicist renowned for his work in electromagnetism. In electrical terms, Hertz signifies the number of times the voltage or current in an AC circuit changes direction each second. 1 Hertz equals 1 cycle per second. The frequency of an AC power supply is measured in Hertz. Now, to specifically address the air handling unit motor scenario where the motor is rated for 1823 RPM at 60 Hz but only achieves 1802 RPM, increasing the frequency above 60 Hz via the variable frequency drive or VFD should indeed raise the motor's RPM. It is important to verify that the motor and the equipment it drives can safely operate at the highest speed. Most motors can tolerate slight overspeeding, but exceeding the manufacturer's limits can cause damage. Before making adjustments, consult the motor's nameplate and the equipment documentation. It would be wise to determine if the 1823 RPM target is critical or if a slightly lower airflow is acceptable. Overspeeding the motor might reduce its lifespan or cause premature wear on connected components like bearings or belts. The relationship between frequency and motor speed is governed by the following formula: revolutions per minute equals 120 times the frequency divided by the number of poles in the motor. From this, it can be seen that the RPM is directly proportional to the frequency. In practical terms, if the goal is to achieve a specific airflow and the current motor speed is insufficient, increasing the frequency is a valid method to explore. Variable frequency drives allow precise control of the motor speed by varying the output frequency. If the motor is rated to handle a slightly higher frequency and the mechanical system can handle the increased speed, then raising the frequency slightly above 60 Hz is a viable solution. The amount of increase needed can be calculated using the proportional relationship, but it should be done incrementally, monitoring the motor's performance and temperature. To elaborate further on Hertz and its impact on motor operation, firstly, understanding the basics of alternating current is crucial. Alternating current, or AC, is a type of electrical current that periodically reverses direction, unlike direct current or DC, which flows in one direction only. The rate at which this reversal occurs is the frequency, measured in Hertz. In a 60 Hz AC system, the current changes direction 60 times per second. Secondly, the frequency of the AC power supply to an AC motor directly influences the motor's synchronous speed. The synchronous speed is the theoretical speed at which the motor's magnetic field rotates. The actual motor speed is slightly less than the synchronous speed due to factors like slip, which is the difference between the synchronous speed and the rotor speed. Thirdly, the number of poles in the motor also affects the synchronous speed. A motor with more poles will have a lower synchronous speed for a given frequency. The number of poles is a design characteristic of the motor and is fixed. Fourthly, the relationship between frequency, number of poles, and synchronous speed is mathematically defined as synchronous speed equals 120 times the frequency divided by the number of poles. This equation highlights the direct proportionality between frequency and synchronous speed. If the frequency increases, the synchronous speed increases proportionally, assuming the number of poles remains constant. Fifthly, in a variable frequency drive application, the VFD controls the frequency of the power supplied to the motor. By adjusting the frequency, the VFD can precisely control the motor's speed. This is particularly useful in applications where variable speed is required, such as in fans, pumps, and compressors. Sixthly, when increasing the frequency to increase the motor speed, it's crucial to stay within the motor's design limits. The motor's nameplate provides important information, including the rated voltage, current, frequency, and speed. Exceeding these limits can lead to overheating, insulation breakdown, and ultimately, motor failure. Seventhly, the VFD also controls the voltage supplied to the motor along with the frequency. The voltage and frequency are typically adjusted proportionally to maintain a constant volts per Hertz ratio. This ensures that the motor receives the appropriate voltage level for the operating frequency, preventing overfluxing or underfluxing of the motor's magnetic core. Eighthly, increasing the frequency beyond the rated value of the motor can lead to several considerations. Firstly, the motor's magnetic core may saturate, leading to increased current draw and heat generation. Secondly, the motor's bearings may not be designed to operate at the higher speed, potentially causing premature wear or failure. Thirdly, the driven equipment, such as a fan or pump, may have its own speed limits. Exceeding these limits can cause damage or performance issues. Ninthly, before increasing the frequency, it's essential to check the motor's and equipment's documentation to determine the allowable speed range. Consult with the manufacturer if there's any uncertainty. It's also advisable to monitor the motor's temperature and current draw to ensure it's operating within safe limits. Tenthly, if a higher speed is consistently required, it might be more appropriate to replace the motor with one that's designed for the desired speed. This can be a more reliable and efficient solution compared to continuously overspeeding a motor beyond its rated limits. The overspeeding of a motor, even slightly, can impact its performance and longevity. Therefore, careful consideration and monitoring are necessary to ensure safe and reliable operation. In the specific scenario of the air handling unit motor, it would be prudent to incrementally increase the frequency while closely monitoring the motor's performance parameters, such as current, voltage, temperature, and vibration. Also, verify that the air handling unit itself can handle the increased airflow without any adverse effects. Furthermore, let's delve deeper into the practical aspects of adjusting the frequency on a VFD to control motor speed. Firstly, safety precautions are paramount. Always ensure that the VFD and motor are properly grounded and that all electrical connections are secure. Disconnect the power supply to the VFD before making any adjustments or inspections. Secondly, familiarize yourself with the VFD user interface and programming parameters. Each VFD model has its own unique setup, so refer to the manufacturer's manual for specific instructions. Thirdly, locate the frequency setting within the VFD menu. This may be labeled as frequency, output frequency, or a similar term. The frequency is typically adjustable in small increments, such as 0.1 Hz or 0.1 Hz. Fourthly, before increasing the frequency, record the motor's baseline performance data, including voltage, current, speed, and temperature. This data will serve as a reference point to compare against after the adjustment. Fifthly, incrementally increase the frequency in small steps. For example, start by increasing the frequency by 0.5 Hz or 1 Hz. After each adjustment, allow the motor to run for a few minutes to stabilize. Sixthly, monitor the motor's performance parameters after each frequency adjustment. Pay close attention to the current draw, voltage balance, motor temperature, and any unusual vibrations or noises. Seventhly, compare the new performance data against the baseline data. If the current draw is significantly higher than before, or if the motor temperature is rising rapidly, it could indicate that the motor is being overloaded or that the frequency is too high. Eighthly, continue making small frequency adjustments and monitoring the motor's performance until the desired speed is achieved. Be mindful of the motor's and equipment's speed limits. Ninthly, once the desired speed is reached, conduct a thorough inspection of the motor and equipment. Check for any signs of overheating, excessive vibration, or unusual wear. Tenthly, document the final frequency setting and the corresponding motor performance data. This information will be valuable for future reference or troubleshooting. It's important to note that the VFD may have other parameters that affect motor speed, such as acceleration and deceleration rates, voltage boost, and slip compensation. These parameters should be adjusted appropriately to optimize motor performance and prevent any issues. Additionally, the VFD may have built-in protection features, such as overcurrent protection, overvoltage protection, and thermal overload protection. These features are designed to protect the motor and VFD from damage in case of abnormal conditions. Ensure that these protection features are properly configured and enabled. If you're not comfortable making these adjustments yourself, it's best to consult with a qualified electrician or VFD technician. They have the expertise and experience to properly configure the VFD and ensure safe and reliable motor operation. In conclusion, increasing the Hertz supply to a motor controlled by a variable frequency drive will increase the motor's revolutions per minute. However, it is imperative to verify the motor and mechanical systems can safely handle the increased speed. Incremental adjustments, careful monitoring, and adherence to safety precautions are necessary for optimal and reliable operation. Remember, frequency is a critical parameter in controlling AC motor speed, and understanding its relationship with RPM is essential for effective motor control. The correct application of Hertz adjustments to a VFD allows for precise speed control, enhancing the performance and efficiency of various industrial and commercial applications. To further extend the discussion, let's explore potential issues and troubleshooting steps when adjusting motor speed with a VFD. Firstly, if the motor does not respond to frequency changes, verify the VFD output voltage and current. Use a multimeter to ensure that the VFD is delivering the correct voltage and current to the motor. If there's no output, or if the voltage or current is significantly low, there might be an issue with the VFD itself, such as a blown fuse or a faulty component. Secondly, if the motor vibrates excessively after increasing the frequency, check the motor's mounting and alignment. Ensure that the motor is securely mounted and that there's no excessive play or looseness. Misalignment can also cause vibrations, so use a laser alignment tool to ensure proper alignment between the motor and the driven equipment. Thirdly, if the motor overheats after increasing the frequency, reduce the frequency back to its original setting and investigate the cause of overheating. Overheating can be caused by several factors, such as overloading, poor ventilation, or faulty motor winding. Check the motor's load to ensure that it's not exceeding its rated capacity. Ensure that the motor's ventilation openings are not blocked and that the motor is receiving adequate airflow. If the motor winding is suspected to be faulty, conduct an insulation resistance test to check for any shorts or grounds. Fourthly, if the VFD trips frequently after increasing the frequency, check the VFD fault codes and refer to the manufacturer's manual for troubleshooting steps. The VFD fault codes can provide valuable information about the cause of the trip. Common causes include overcurrent, overvoltage, undervoltage, and ground fault. Investigate the specific fault code and take appropriate corrective actions, such as adjusting the VFD parameters or addressing any underlying electrical issues. Fifthly, if the motor speed fluctuates erratically after increasing the frequency, check the VFD control settings and wiring connections. Ensure that the VFD is properly configured for the motor type and application. Verify that all wiring connections between the VFD and the motor are secure and that there are no loose or corroded terminals. Electrical noise or interference can also cause speed fluctuations, so use shielded cables and proper grounding techniques to minimize noise. Sixthly, if the motor produces unusual noises after increasing the frequency, inspect the motor's bearings and lubrication. Worn or damaged bearings can cause unusual noises, such as squealing, grinding, or knocking. Lubricate the bearings according to the manufacturer's recommendations. If the noises persist, the bearings might need to be replaced. Seventhly, if the motor runs in the wrong direction after increasing the frequency, reverse the motor's phase sequence. Swap any two of the 3 motor leads connected to the VFD to change the motor's direction of rotation. Eighthly, if the motor's performance is sluggish or unresponsive after increasing the frequency, check the VFD acceleration and deceleration rates. The acceleration and deceleration rates determine how quickly the motor speed changes. If these rates are set too low, the motor might take a long time to reach the desired speed. Increase the acceleration and deceleration rates gradually to improve the motor's responsiveness. Ninthly, if the motor stalls or fails to start after increasing the frequency, check the VFD starting torque settings. The starting torque is the amount of torque that the motor can produce at startup. If this starting torque is insufficient, the motor might not be able to overcome the load's inertia and stall. Increase the VFD starting torque settings to improve the motor's ability to start under load. 10thly, if you're unable to resolve the issue yourself, consult with a qualified electrician or VFD technician. They have the expertise and specialized tools to diagnose and repair complex VFD and motor problems. In addition to these troubleshooting steps, it's also important to perform regular maintenance on the VFD and motor to prevent issues from occurring in the first place. Regular maintenance tasks include cleaning the VFD cooling fans, inspecting the wiring connections, and lubricating the motor's bearings. By following these troubleshooting steps and performing regular maintenance, you can ensure the safe and reliable operation of your VFD and motor system. Now, let's consider the scenario where the air handling unit motor is consistently running at a frequency higher than 60 Hz to achieve the required airflow. Firstly, assess the long-term implications of operating the motor at an elevated frequency. While it may provide the necessary airflow, it could potentially reduce the motor's lifespan and increase energy consumption. Secondly, evaluate the possibility of replacing the motor with a model that's better suited for the required airflow. A larger or more efficient motor might be able to deliver the necessary airflow without needing to be overspeeded. Thirdly, consider optimizing the air handling unit's ductwork and dampers. Improving the airflow efficiency of the system can reduce the demand on the motor and potentially allow it to operate at a lower frequency. Fourthly, explore the use of variable air volume or VAV systems. VAV systems automatically adjust the airflow based on the building's needs, which can reduce energy consumption and improve comfort. Fifthly, consult with a mechanical engineer or HVAC specialist to evaluate the overall system design and identify potential improvements. They can provide valuable insights and recommendations based on their expertise. Sixthly, conduct a cost-benefit analysis of the different options. Compare the costs of replacing the motor, optimizing the ductwork, or implementing a VAV system against the potential energy savings and improved system performance. Seventhly, factor in the environmental impact of each option. Consider the energy consumption, greenhouse gas emissions, and resource usage associated with each solution. Eighthly, choose the solution that provides the best balance of performance, costs, and environmental impact. Prioritize options that are energy efficient, sustainable, and cost-effective over the long term. Ninthly, implement the chosen solution and monitor its performance. Track the energy consumption, airflow, and motor performance to ensure that the system is operating as intended. Tenthly, make adjustments as needed to optimize the system's performance. Fine-tune the VFD settings, adjust the ductwork dampers, or modify the VAV system parameters to achieve the desired results. It's important to remember that HVAC systems are complex and interconnected. Changes to one component can affect the performance of other components. Therefore, it's crucial to take a holistic approach and consider the entire system when making any modifications. Regular monitoring and maintenance are also essential to ensure that the system continues to operate efficiently and reliably over time. By carefully evaluating the options and implementing the right solution, you can optimize the air handling unit's performance, reduce energy consumption, and improve the overall comfort of the building. Moreover, in certain applications, encoder feedback can be incorporated into the VFD system to provide even more precise speed control. An encoder is a device that provides feedback to the VFD about the actual motor speed. This feedback allows the VFD to compensate for any variations in load or voltage or maintain a constant speed. Encoder feedback is particularly useful in applications where precise speed control is critical, such as in printing presses, textile machinery, and material handling systems. The encoder is typically mounted on the motor shaft and generates a series of pulses that are proportional to the motor speed. The VFD uses these pulses to calculate the actual motor speed and adjust its output frequency accordingly. There are two main types of encoders: incremental encoders and absolute encoders. Incremental encoders provide relative position information, while absolute encoders provide absolute position information. Incremental encoders are simpler and less expensive than absolute encoders, but they require a reference point to determine the absolute position. Absolute encoders are more complex and expensive, but they provide absolute position information without needing a reference point. When selecting an encoder for a VFD system, it's important to consider the required accuracy, resolution, and speed range. The accuracy of the encoder determines how precisely it can measure the motor speed. The resolution of the encoder determines the number of pulses it generates per revolution. The speed range of the encoder determines the maximum speed at which it can operate. In addition to encoder feedback, some VFD also offer other advanced control features, such as sensorless vector control and direct torque control. Sensorless vector control estimates the motor's flux and torque without using an encoder. Direct torque control directly controls the motor's torque by adjusting the voltage and current. These advanced control features can improve the motor's performance, efficiency, and stability. However, they also require more complex VFD configurations and tuning. When implementing a VFD system with advanced control features, it's important to follow the manufacturer's recommendations and consult with a qualified VFD technician. They can help you properly configure the VFD and optimize its performance for your specific application. Furthermore, it's worth mentioning the importance of harmonic mitigation in VFD systems. VFD can generate harmonic currents, which are distortion components of the electrical current at frequencies that are multiples of the fundamental frequency 60 Hz. These harmonic currents can cause various problems, such as overheating of transformers and conductors, malfunctioning of sensitive electronic equipment, and increased energy losses. To mitigate harmonic currents, various techniques can be used, such as installing harmonic filters, using multi-pulse VFD, and using active front-end VFD. Harmonic filters are passive devices that are designed to block harmonic currents from flowing into the power system. Multi-pulse VFD use multiple rectifier bridges to reduce harmonic current generation. Active front-end VFD use active components to cancel out harmonic currents. The choice of harmonic mitigation technique depends on the level of harmonic distortion, the cost, and the space constraints. It's important to conduct a harmonic analysis to determine the level of harmonic distortion and select the appropriate mitigation technique. Harmonic analysis can be performed using specialized software or hardware. It's also important to comply with the applicable harmonic standards, such as Institute of Electrical and Electronics Engineers Standard 519. This standard sets limits on the amount of harmonic distortion that is allowed in power systems. By implementing appropriate harmonic mitigation techniques, you can ensure the reliable and efficient operation of your VFD system and prevent any problems caused by harmonic currents. In addition, proper grounding is essential for the safe and reliable operation of VFD systems. VFD can generate high-frequency noise and transient voltages, which can cause electrical interference and equipment damage. Proper grounding provides a low impedance path for these noise and transient voltages to return to the source, minimizing their impact on other equipment. The grounding system should be designed and installed in accordance with the applicable electrical codes and standards, such as the National Electrical Code or NEC. The grounding conductor should be sized appropriately to handle the expected fault current. The grounding connection should be clean and tight to ensure a low impedance path. It's also important to use shielded cables for the motor leads to minimize electrical noise. The cable shield should be grounded at both ends to provide a continuous shield. In addition to grounding, surge protection is also important for VFD systems. Surge protection devices or SPD can protect the VFD from damage caused by voltage surges or spikes. Voltage surges can be caused by lightning strikes, switching operations, or other electrical disturbances. SPD should be installed at the VFD input terminals to protect it from incoming surges. The SPD should be rated appropriately for the expected surge voltage and current. It's also important to coordinate the SPD with the other protective devices in the electrical system to ensure proper protection. By implementing proper grounding and surge protection techniques, you can protect your VFD system from electrical noise, transient voltages, and voltage surges, ensuring its safe and reliable operation. And lastly, remember to always prioritize safety when working with VFD systems. VFD can operate at high voltages and currents, which can be dangerous if not handled properly. Always disconnect the power supply to the VFD before making any adjustments or inspections. Use proper personal protective equipment or PPE, such as safety glasses, gloves, and insulated tools. Follow all applicable safety procedures and regulations. If you're not comfortable working with VFD, consult with a qualified electrician or VFD technician. They have the expertise and experience to safely and properly install, maintain, and repair VFD systems. By following these safety precautions, you can protect yourself from electrical hazards and ensure a safe working environment.